Hello, my name is Robert Smith and I'm with New River Community College's Academic Assistants, and today we are looking at crystal structures. And we're specifically asked to calculate the atomic radius of silver in picometers for a silver that crystallizes with a face-centered cubic cell and has a density of 10.5 grams per cubic centimeter. So the first thing we have to recognize is what information are we given and how we can use that information to get to where we need to go. What we need to get to is the atomic radius. And if you recall, we're going to call that R. So let's say R is equal to question mark. That's our end goal. And we need to make sure it's in picometers, but we can deal with that at the end. And what are we given in order to achieve this goal is we're given the density, and we're given the fact that it's a crystal with a face-centered cubic unit cell. So all of that information is going to be useful in calculating our atomic radius. So let's get started. The first thing you're going to want to do is take the information that you're given and use it to try to accommodate your value that you're looking for. Okay, so what we know about a face-centered cubic cell is that we have parts of an atom in this unit cell. And ultimately, the parts are going to lead to a total number of a given atom. So we know that there are 8 1/8 atoms, and they're in the corners. They're the corners of the cell. And there are 8 corners to a cube, and each of them is occupied by 1/8 of an atom. And to that, we're going to add 6 half atoms. Each side, there are 6 sides to a cube, and each side on the face, on the center of it, holds half of an atom. It's as though you took a cross-sampling created a unit cell, and by doing so you sliced up these atoms into pieces that are easily measured. So there are 6 atoms, or 6 half atoms rather. And 6 times 1/2 is 3, and 8 times 1/8 is 1. Therefore we have 4 total atoms. So that is what we can gather from our face-centered cubic unit cell. The other thing we're going to get from it is the formula for area with respect to radius. But we will come to that here near the end. So the next thing we're going to do is we're going to take that information about the 4 atoms, and we're going to relate that to a unit cell in order to figure out how many grams we have of silver in a unit cell. So all it is a little dimensional analysis. So we've got the mass of the unit cell is going to equal 4 atoms per unit cell, per 1 unit cell, and we're going to multiply that by Avogadro's number with relation to the moles. So we want to find out what 1 mole of these particular atoms are. So okay. And then we can use the molar mass of silver to figure out the actual mass of the unit cell. So, if you note, again with dimensional analysis, we have our atoms that cancel out, we have our moles that cancel out, and we're left with grams per unit cell. And when you do the arithmetic out, you'll find 7.167 times 10 to the minus 22 grams per unit cell. We're going to call that UC. But because we're only dealing with one unit cell, we can then take that information and multiply it by 1 unit cell. So ultimately, our mass is 7.167 times 10 to the minus 22 grams. Now, if we didn't know, if we were told a different number, we had several unit cells, then you can multiply it by whatever number of unit cells are being addressed in this problem. However, for our ourselves, all we have to do is multiply by 1 unit cell because that's all we're dealing with. And the result is 7.167 times 10 to the minus 22 grams. Okay, so now we have the mass. And we have the density from our problem itself. So if I move this up just a tiny bit, what we can get from mass and density, if you go back to chapter 1 in your book, you can find volume from mass and density. Volume is equal to mass over density. So for this equation, you got 7.167 times 10 to the minus 22 grams all over 10.5 grams per cubic centimeter. So this will give us our volume in cubic centimeters. As you'll find that grams and grams cancel one another out. So the result is 6.826 times 10 to the minus 23 cubic centimeters. So the other thing to recognize is knowing what a face-centered cubic unit cell, we can have an equation for area based off of volume and then an equation for radius based off of area. So, edit. So, knowing that it's a face-centered cubic unit cell, we can then take our volume information and with it we can calculate the width of a side, which they refer to in your book as the little a. Little a is equal to the cube root of volume in the case of the face-centered cubic cell, unit cell, which in this case would be the cube root of 6.826 times 10 to the minus 23 cubic centimeters, which is equal to 4.087 times 10 to the minus 8 centimeters. So now that we have the side, we can again refer back to the face-centered cubic unit cell and what we know, what formulas we know from that particular unit cell. And moving this up slightly, we can find that A is also equal to the square root of 8 times the radius. And radius is what we want. So we're going to readdress that. We're going to rearrange it using algebra and find that radius is going to equal our width over the square root of 8, which would be 4.087 times 10 to the minus 8 centimeters over the square root of 8, which if you do that out is 1.445 times 10 to the minus 8 centimeters. But we don't want it in centimeters. We want it in picometers. So we're going to relate it back to picometers using dimensional analysis. Again, we're going to move this up slightly. So R is equal to 1.445 times 10 to the minus 8 centimeters. And for every 1 meter, there are 100 centimeters. And there are 1 times 10 to the 12th power picometers per every 1 meter. And if you look, centimeters and centimeters cancel out, meters and meters cancel out, and you're left with picometers, which would equal 144.5 picometers. And that is our final answer, 144.5 picometers.